What up, nerds? Today we're checking out the distance between points. It's a Pythagorean theorem and distance formula. So what I'd like you to try is to plot these points A, B, C, and D on your fancy note sheet, and then think about what the distance between D and C is, what the distance between B and C is, and then maybe what the distance between D and B is. That one's a little tricky. It's the whole idea for this unit. So pause me and try that. Go. All right, so if you plotted that, they look like this. They're somewhere around here. There we go. A is here. It's 8 in the x and 3 in the y. So you go backwards 8 and up 3. B is forwards 4 and up 3, 4, 2, negative 2, sorry, and negative 8, negative 2. So they should look like that. So the distance between D and C, between here and here, right, these points, is fairly straightforward. Think about how far you'd have to walk. Well, this is at negative 8, so you'd have to walk 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4 more. So 8, 9, 10, 11, 12. So this is 12 units, right? So this is 12. Great. The distance between B and C is, well, you'd have to go from B to C or C to B. It doesn't really matter. 1, 2, 3, 4, 5. Right? There were 2 here and 3 here. So in total, this thing is 5, right? Units. And same thing here. This was, let's see, let's do this in a little bit different color. This was at negative 8. So from negative 8 to the axis, that's 8 units. And this point C was at positive 4, so it's 8 and then 4 more units. And so that's where we get our 12. The fussy bit comes in if you're trying to find the distance between D and B, right? It's here, that's here. If we make a, let's try this. Let's do it in some ridiculous color. How about, let's try pink. Not that pink's a ridiculous color, but let's throw down a line and see what happens with this. If we take this distance, it's hard to figure out how far that is because I can't count along the squares, right? So if we lock this as a certain length, I can't really figure out how long it is, right? You'd have to like turn this whole thing. I don't know how you'd do it. It'd be messy, right? It'd be really messy. Let's see if we can do this. So you'd have to do like that, right? And then count from here to there. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? Man, there's got to be some better way than that. And there is. And it's called the Pythagorean Theorem and the distance formula. And that's where we're going. So, because you don't always have fancy graphs that can spin. That kind of makes me dizzy. Let's try it out. So, if you, on your next sheet, you have some squares. And you'll notice that this happens. If you take a triangle, let's go back a little bit. You take a right triangle, right? It's got a right angle. And who cares about the other angles? This is a right triangle. If you take this length, right? If you take this length A and you run the same distance out and make a box. So if this length is A and this length is A and this length is A and this length is A, right? This becomes a box that's A squared. The area there is A times A, so it's A squared. Same, if you do the same thing with C, like this is C and so is this, so then this box has C squared as its area, right? If you have a 3 by 3 box, 1, 2, 1, 2, this is 3 by 3, you have 1, 2, 3, 4, 5, 6, 7, 8, 9 squares. So the area is the side length squared, which is 9. I don't know the side length, it's just called C, so I'm going to call it C squared. So therefore, this area is B squared. Great. If you happen to fill those in, so this is A, and so this is a square with length A, and same with B, and same with C. We're going to do this in class in physical format. next time I see you. But if you break this up nicely, if you cut this piece up, if you cut B up and arrange it nicely, Pythagoras, an interesting guy, was one of many mathematicians who noticed this property, that these fit perfectly in here, and you just have enough room for A squared. So what the Pythagorean theorem is that if you take a right triangle and you make squares out of the sides, they call it the legs, right? You make squares out of the sides. The two short areas will fit into the big area perfectly. Yeah? So that's my key concept. The area of the squares of the smaller two sides of the right triangle equals the square, the area of the square of the next one. Now that doesn't sound very useful for this, but we'll get there, right? So I'd like you, if you haven't, to make sure you have this down in your notes, that the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. The hypotenuse is the longest piece. The other ones are just the sides, the legs. And so we will often write this like this in an equation form. We'll say c squared, the big square, is equal to the two smaller squares added together, right? Just like this. So, if we go back to our original, let's go back to our original triangle, right? And let's keep this guy. Let's bring him here and move this back to our warm-up. Here's our warm-up guy. Let's get rid of the grid. Let's get rid of some of this other stuff so we can see it. I know from Pythagorean theorem that if we make a square, this is 5 units, if we made this square 5 units, and we made this 12 by 12, and we didn't know this piece, but it's really big, right? Let's call this C. I know that this square, 12 squared, that area, and 5 squared, this area, would equal c squared, right? So we can throw this into an equation instead of just doing it graphically, which nobody has time for. Let's use Pythagorean theorem, which is this idea. So we know the big square, I don't know what it is, it's called c squared, should be equal to the two smaller squares added up. Grab your fancy calculator if you need, and crunch this side. This is 25 and 144, and that sounds like 169, and so that's c squared, right? It's still, this is the size of this area. So I don't want c squared, I just want c. So we got to take the square root of both sides. Bam, bam, and you're left with the c, the root and the square cancel, and you're left with c is root 169, which is 13, which, just like we measured with when we turned the grid sideways, so that length is 13. Ka-ching, we got it. All right. What I'd like you to do is try this idea. In a second, you're going to pause me. You can try A, B, C, and D. Use the idea behind Pythagorean theorem that the big side squared should be the squares of the two smaller sides added up. Think about which one's the long side. C squared is always the hypotenuse. It's always the long side. So make sure you're doing that and show me your work. Okay, pause me and go. All right, so in example A, right, let's call this one A, this side A, and this side B. It really doesn't matter which one you call. They're interchangeable, right? But the longest side is always across from the 90-degree angle. This side is C. So I know that A squared plus B squared should be C squared. I know it takes one more second to write out the equation like this, but write out the equation. You won't mess it up that way, right? So here's A, plug it in. 3, where A should be, right? 3 squared. And here's B, 4 squared. And here's C. Oh, I don't know C, right? So we square it. 3 squared is 9, 4 squared is 16, that's c squared, and so this is 25, and so c squared should be 25. You take the square root of both sides, and you get 5. You get plus or minus 5, but still 5. And lo and behold, ping, 5. Great. Try it again over here. Let's use some purple. Purple. Go along with the same side lengths. Let's move me out of the way. Still here. So this is 6 squared. Bad. We want the two short sides squared equals the long side squared. This is the long side because it's across from the 90-degree angle. So you get 6 squared and 8 squared is the long side squared. This is 36. This is 64. And you get c squared. This is 100. Lo and behold, and c should be, take the square root of both sides, and c should be 10, right? We're just going square root, just like this. We went square root, and c should be 10, and bam, there it is. Well, here, let's show you this one. Maybe you got the trick, maybe you didn't. If you didn't get the trick, this is why. So we know that this should be a squared plus b squared equals c squared, right? This is one of the side lengths. Let's call it a. This is the hypotenuse. It's across from the 90-degree angle, right? Be careful, right? So we're given a and c, and we're looking for b. So I know that a is 5 squared. I don't know b squared. And c is 13 squared, right? So 5 squared plus b squared equals 13 squared. Clean it up, right? 5 squared is 25. 13 squared is 169. And if you now you got to subtract 25 off of both sides. And what you get 144, I think. And then when you take the square root of both sides, root, I think you get 12. Cool, plus or minus 12. And there it is. Sweet. All right. D. Anybody? You can't use Pythagorean theorem on D because I don't know if this is a right triangle, and it specifically doesn't look like a right triangle. So because of that, this is a dirty trick, and it's not a right triangle. I can't apply Pythagorean theorem. So maybe there is a way to find this length, but we either need to know like the angle or we need some other information. So we can't figure out that because it's not a right triangle. No right angle. Yeah? Sad kitty. Tear. Moving on. Make sure they're right triangles. All right. So I guess we already did this. We figured out the distance between D and B, and we did that by saying, oh, this length was 12, this length was 5, so this length should be 12 squared plus 5 squared, and that should give us this DB length squared, right? And we figured out that this was the DB was 13. All right. So one way to do this is this is called the distance formula, and it shows you the distance between points, right? And it looks awful, x's and y's and squareds, but it's just the distance. It's just Pythagorean theorem in a bad Halloween costume. So if you started with a squared plus b squared equals c squared, each of these points is going to have an x and a y coordinate. So let's call this x1, y1, and this one will be x2. Let's do it in a different color. Let's do x2 comma y2. So if you're going from here to here, you're trying to find the distance between m and n. One way to do that is find a squared plus b squared equals c squared. Yeah, and a is really made up of this distance, 1, 2, 3, 4. Well, this point is 2 over and 1 up. And this point is 1, 2, 3, 4, 5, 6 over and 1, 2, 3, 4 up. So 6 over and 4 up. I would really like to not have to count these. I'd like somebody to just be able to give me 2, 1 and 6, 4 and have this, be able to find the distance between those. We know that this horizontal distance is just the difference in the x values, right? You should get 1, 2, 3, 4. If you subtract 6 minus 2, you subtract the 2x values, right? Then you'll get that distance, and you square it. That's all a is the 2x values, the difference between them, and then you square it. Same thing with b. This short side is the you'd have to go up from here 1, 2, 3. Well, you get 3 from starting at 1 and going to 4, right? Or another way to think about it is subtracting 4 minus 1, right? That's what distance is. So b is y2 minus y1 squared, and that gives us c squared. This big square root is from getting rid of this square. So if we take the square root of this side and we take the square root of this whole side, you're just left with c. So if we wanted to use the distance formula on this idea, you'd say, all right, well, I want the distance between m and n. Let's take the square root of the change in the x values. Well, it goes from 2 over to 6. Those are the 2 x values. So you'd say 6 minus 2 to find the difference between those. And then it goes from 1 up to 4. To find the difference between those, you'd say 4 minus 1. Square it. Cool. So that gives you, what, 4 squared plus 3 squared. Roll it down a little bit. So you get 16 and 9. And that's c. And that's what 16 and 9 is, what, 25? And, oh, sweet. So c ends up being 5. Cool. All right, so that's the ball game. Yeah, okay. That's the ball game, and when you roll in, I'm going to give you something like this, right? Or maybe like this. Try the practice problems on your sheet, and I'll see you then. Bye.